All right, we're going to move on to related rates today, and it combines the last two topics. So, 2 topics ago, we looked at finding maximum and minimum areas, volumes, perimeters, things like that. Yesterday, we looked at rates of distance. So, you do the derivative of distance with respect to time, that gives you velocity. Derivative of velocity with respect to time gives you acceleration, and so on. So, we're going to kind of mix the two together. So, it'll be dealing with shapes, so we'll get things such as a cone that have a radius and it would have a height. So the cone, if we fill it full of water or something like that, we'd have a volume. But instead of it being maximum volume or something like that, we're going to be looking at what rate would the volume change if the radius and the height were changing at a certain rate. So a rate is just sort of another way of finding a slope or a derivative. So what we're looking at is, can we use derivatives to calculate the speed or the rate that a volume is changing compared to a length like a radius? So without calculus, these kind of questions are almost impossible to solve, but with derivatives, it actually works quite well. So how we approach this is we're trying to solve for problems where we're going to calculate the instantaneous rate or slope of one quantity if we are given the rate or slope of another. And in practical terms, often you can usually calculate one or determine one, and that you can use that one to help you solve for the other. For these things, I'll just randomly give you one and ask for the other. It doesn't really matter too much. And the idea or the method that we're going to use is we're going to use implicit derivatives, but instead of doing implicit with respect to x, we're going to be solving our derivatives with respect to time. So for example, if I gave you something like area equals pi r squared, we're going to do the derivative of the equation with respect to time. So we'd calculate derivative area with respect to time. So that means we'd have to do the other side with respect to time, but r is our variable. So we could calculate the derivative area with respect to r, but that's not what we're looking for. So using a chain rule, we'd have to times it by dr dt. And some people think, well, it's kind of like canceling units, so that actually makes sense. So what we're going to be doing, it looks very similar to when we did implicit. So if I gave you something like y equals 3y squared, and I said do this implicitly, we went dy dx on the one side, we did the derivative of 3y squared with respect to y, which gave us 6y, and then we had to times it by dy dx. So we use sort of the same idea. So for this one, our derivative of pi r squared would be 2 pi r, but we don't want r as our variable, we want t, so we would times it by dr dt. So that's the method we're going to use for these questions. So this first example, we have a square. So let's draw a square, let's label each side x. So the area of the square would just be x squared. Okay. So that's pretty easy. So now we want to calculate the rates. So we'll do the derivative of area with respect to time. We'll do the derivative of x with respect to x. So the derivative of x squared would be 2x, but we don't want x, so we'd have to multiply it by dx dt. And that's it. So now we just plug in the numbers and solve. So if you go back to the question, it says our side length is increasing at 2 centimeters per minute. So that would be the dx dt. We won't worry about the units, we'll put those in at the end. The question's asking for the area, so we're looking to solve for dA dt. And the rest of our formula is 2 times x, and you can see in this case it's saying determine the rate when x equals 10. So we just plug the 10 in and we're done. So we'd have 2 times 2 times 10, which would be 40. Go back to the question, it'd be centimeters squared per minute would be our units. So what that means is, as this x is increasing at 2 centimeters per minute per side, once it gets to the size of 10 by 10, it's now growing at a rate of 40 centimeters squared per minute in terms of our area. So when we're working with these equations, we can substitute the numbers in, but we got to be careful. If things are changing, we can't substitute until after we do our derivative equation. Once the derivative is done, then we can substitute. So this next question is similar, except it's a volume. So we have a spherical balloon, and we're going to be pumping in air. So they give us a rate of volume. So the 100 would be our dV dt. So now what we have to do is calculate the dr dt. So we have our equation, do our implicit derivatives. So we'd have dV dt Derivative of 4/3 pi r cubed would be 4 pi r squared. And because it's an r, we would times it by dr dt. And now we're ready to substitute. So the 100 would be our volume rate. Our dr dt is what we're looking for. And the rest of our formula has 4 pi times r squared. So at this particular moment in time, it gives us a diameter of 50. So that means our radius would be 25. So we'd plug 25 in there and we're done. So now we just rearrange the equation and solve for dr dt. So 4 times 25 squared would be 2500. And simplify 100 divided by 2500. I'll just leave it as a fraction. We could write it as 1 over 25 pi, and that would be centimeters per second. And you can leave it as a fraction like that if you want. You could divide it on your calculator and get a decimal of 0.0125 or whatever it would end up being. Decimals, fractions, really doesn't matter how you do these questions. So our next example is a little bit different because we have a cylinder. So in this case, we're going to have a cylinder, and for cylinders, our volume formula is pi r squared h. So we have a radius and we have a height, and together those would give us our volume. So the problem in this case is we have three variables. So if you go back to the notes, I said we'll use the derivative rate of one given to us to help us solve the other. So we're not able to do derivative equations with three variables. We can do them, we can do product rule and things like that, but we don't have enough information in the question to solve for three. We can only solve for two. So what we have to do is we have to be able to get rid of one of the variables. So if we were to fill, this question is saying fill this cylinder full of water, so it doesn't really matter what height the water's at, it's because it's cylindrical shaped and it's consistent throughout the whole thing, our radius is really never changing. So this formula is for constant numbers. We can plug in any kind of constant numbers right off the start. And no matter where we are for the height of this water, the radius will always be 2 meters. So we should actually plug the 2 in first. So that would simplify to just 4 pi h. So because it's constant, we can do that. But the rest of the things are changing. Our volume is changing, our height is changing. So we can't do any more substitutions until after we do our derivatives. So now if we do the derivative of volume, we get dv dt. Derivative of 4 pi h would be 4 pi. But because it's h, we need to times it by dh dt. So the original formula works for constant values. We have to use the derivative formula for any value that's changing. And once we keep that separate, the rest of these questions work pretty good. So for this one, we're looking for dh dt. They give us dv dt is 2. So for this case, we should get, if we solve for dh dt, we would have 2 divided by 4 pi. Or we could simplify it to just 1 divided by 2 pi. And our units would be, it's a height, so it'd be meters per minute. And that should be it. So you got to be really careful of what the formula is, do your implicit derivatives, plug in the numbers at the appropriate time. So if it stays constant, put it in at the beginning. If it's changing, do it after you do your derivative calculation. Okay, here's another question that's similar. Kind of shape, whether it's an only thing I changed in this case is our original shape is calculate these rates. So it's the same radius of 2, that's all for today. We still have the same height of 4. And for cones, we do the vertical height, not the slanted side. And everything else is the same. So what makes this one a little bit more complicated is our radius is not constant anymore, right? As we get this thing more and more water inside, the cone shape will get bigger and bigger and bigger. It doesn't change the shape of the cone, it's just the height and the radius and the volume are changing. So when we use our formula for a cone, which is 1/3 pi r squared h, we can't plug anything in yet because nothing stays constant. But what we can do is no matter what height the water level would be, we still have something that's consistent between these two things. So if in my big black triangle I have a height and a width of 2 and 4, we can see that if I do a smaller triangle, we'd still have the same bottom angle. Those angles aren't changing. They'd both still be 90-degree angles. So that means the other two angles would also be the same. which means we have similar triangles. And if you remember from junior high, similar triangles have equal proportions between the sides. So that means for this case, if I was to calculate the radius to height, it'll always be in a 2 to 4 ratio, or we could solve it for r, which would mean r would equal 2/4 h, or more specifically 1/2 h, or we could solve for h, and that would be 4r over 2, or we could simplify that to 2r. So depending on which one we're solving for, we can now substitute these into our original equation. So if we look back at the original equation, it's asking us to calculate the rate the water level is rising. So we're looking for dH dt. So if we're looking for h, we want to eliminate the r. So that means we can plug in our 1/2 h into our equation. So we still want to do this before we do our derivatives because we've got to get it down to two variables. So we'd have 1/3 pi times 1/2 h squared times h. Now what we want to do is simplify that. So we'd have 1/3 pi, half squared would be 1/4, h squared times h. So that should simplify to 1/12 pi h cubed. So even though the r wasn't constant, it is an equal ratio, so we can substitute that in first. Now we're good to do our derivatives. So the derivative of volume with respect to time, derivative of the other side, 3 times 1/12 would be 1/4 pi h squared times dH dt, because it's not a t. And now we're ready to plug in our values. So the question again, they give us the volume as being 2. We have 1/4 pi, and it's asking us to calculate the rate when it's 3 meters deep. So our height would be 3, and we can solve for dH dt again. So if we simplify this, we'd get 2 equals 9/4 pi, times dH dt. So if we rearrange that, dH dt would equal 2 divided by 9/4 would be the same thing as 8 divided by 9 pi. So that should be our final answer as a fraction, and we can put in our units. Again, its height to be meters per minute. So 8 divided by 9 pi would be a good enough answer for that one. And that's basically it. So if you look at look at my next page, you can see the cone, the radius and the height stay consistent. So we plug that in. So you can see we got 1/12 pi h cubed. Do the derivative of that and simplify, and we get our answer. Okay, so it works pretty good. We didn't have to do any extra work. That last page is